So today, got a little simple one. Pretty much amount of substances, which is like physical chemistry. I've already started halfway through a question, but I'm just really bored, so I thought I might just do a question. So get question B of a question said 0.143 grams of gaseous sample of ammonia occupied a volume of 2.86 times 10 to the power of minus 4 meters cubed at a temperature of T and a pressure of 100 kilopascals or 100,000 pascals of pressure. State the ideal gas equation, calculate the number of moles of ammonia present, and deduce the value of the temperature T. So the gas constant always 8.31. Ideal gas equation is PV is equal to nRT. I didn't read the question, and I just assumed when I saw moles of ammonia, I just wrote down how to calculate and just, rearrange the equation. And I realized that T was there, so maybe something was missing. Realized that the question was asking, well, I need to find out what the actual moles is through mass here and over MR. So 0.143 divided by 17, that should give you 8.41 times 10 to the power minus 3, or they give you 3 significant figures. So yeah, just put it down. 0.41 times 10 to the power of minus 3 moles. Now we have that, we can calculate what T is. Should probably just say for the video, so T will be in Kelvin, R in that, so we do that for you. Pressure is always in just pascals, not kilopascals. Volumes in meters cubed, not decimeters cubed. And we already have that, just normal moles. And yeah, so to get T, we rearrange the equation. So T is equal to PV over NR. And then you get, so for example, T here would be equal to, just do that. So it'll be the pressure, 100,000 times by the volume, which would be 2.86 times 10 to the power of minus 4. 86 times 10 to the power of minus 4. All of that over the moles we just worked out, so 8.41 times 10 to the power of minus 3 by R, which is 8.31. And T would be equal to 100,000. So just basically just work that out, which should be simple. 100, put it closer. Yeah, 100,000. Temperature will be 409. Just say Kelvin. I don't think it's already in 3 significant figures, so 409. Double check it. Yep. Let's just see the mark scheme. Mark scheme also says anywhere between 408. Let's get it here for you. Anywhere between 408 and 410.5, or 408.5 to 410.5. So 409 is just what we need it to be. And yeah, it also says remember to put in the right number of significant figures as your final answer. Don't round when you get to your in terms of when you're actually substituting into the equation. Like, make sure you put in the values that you have here, or the exact value, and then when you get to your final answer, you add in the actual value, or the 3 significant value, I guess. So yeah. Compound A is an oxide of sulfur at 415 Kelvin at gaseous sample of A. of mass 0.304 grams occupied a volume of 127 centimeters cubed at pressure of 103 kilopascals. State the ideal gas equation and use it to calculate the number of moles of A in the sample and hence calculate the relative molecular mass of A. Ideal gas equation that should just know it off by heart. So they want is actually, what do they want? Next starting off. So they want you to calculate the number of moles of A in the sample, calculate the relative molecular mass of A. So that's the case. So I want you to find out this and use that to find the MR essentially. So N equals PV over RT. N would be equal to the pressure, which is 103,000 times by the volume, which was 127 centimeters. No, that's not it. That's not it. 127. Yeah. 27 times by 100 to get you, because you have to get it to meters cubed. So just times that by 100. All of that over RT. So 8.31 times by 415 Kelvin. N should be equal to, so just put that in, times by, this should be divided by, now that I think about it, to get from centimeters cubed to meters cubed, you usually divide it by 1000 instead of, yeah, you should divide it. It's not, that's my bad, it's divide. So 103 divided by 127 divided by 100 all over 8.31 times by 415. That seems a little bit too big for mole value, so double check it. 127 to get from centimeters cubed to meters cubed, divide by 1000, not 100. If you make a mistake, like, look at your answer, I guess, and then you can see if you've made the wrong answer. So you can see here 3.79 sounds more like a more realistic answer for your mole value. So yeah, so you just probably say 3.79 times 10 to the power of if you're giving it divided by 1000. So let me just double check this here. Should be, that makes more sense, yeah. It's a cubed value, so you have to make sure your 100 is cubed. I know I'm making a lot of mistakes here, but you should make sure that it's 100 cubed. So I'll get rid of this here, because it's not a scale value. It's actually to you're talking about volume, not just area or just normal size. So you have to make sure it's cubing it. So it would be 100 cubed, which is what you divide that by, and that should give you 3.79 times 10 to the power of -3 moles. Once you get that, you do moles is equal to, we're trying to find the MR. moles is equal to mass over mR, sorry. Trying to get mR, so mass over the moles, and that equals the mR. So your mR should be equal to 0.304 grams, which is what they give you here. Divide that by your moles, which would be 3.79 times 10 to the power of minus 3. And that will equal, no, I'll just put in now. MR is 80.21. But since you're talking about, to see how many significant, you have to check how many significant figures you have. So 3 significant figures, 3 significant figures, 3 significant figures, 3 significant figures. But you should look for your lowest amounts of significant figures, which in this case is still 3. So you can just take out that one here, so just 80.2, and that would be your MRRFM. Yeah, we've got this. So calculate. So a hydrocarbon W contains 92.3% carbon biomass. The relative molecular mass of W is 78. Calculate the empirical formula of W. So we have hydrocarbon. So it always tells you don't need to know. So hydrocarbons are only carbon and hydrogen. It doesn't say halogen or alkane or anything else specific. It just says hydrocarbon, so you can assume it's just carbon, hydrogen. So here you can just say your carbon is equal to 92.3%, but you can have it as out of 100 grams because it's a percentage, so it's out of 100. So you can say this as over 100 grams. Also out of 100 grams, and that's out of carbon. So to get your hydrogen here, just do simple 100 minus 92.3, and that gets you 7.7, I believe. Am I wrong? Should just be 7.7. There you go. So yeah, 7.7. All right, 7.7. You divide this by its atomic mass, which is just 1. This is 12. It's 12.011, but in this case, you can get away with just having normal, which is just 12. 92.3, so we just divide that by 2, so 92.3 over 12. That gets you 7.6911, so 7.691. One thing, this is only a small question, but one thing I always do is I have the exact value on the side, because usually you have like 3 or 4 of these. Because you have 3 or 4 of these, and you're trying to find, you kind of get lowest value, and you don't want to use the simplified version or the rounded version until like the end. So I always write the exact value on the side. So 900. You don't have to do this, but if you want to have a very exact answer, just have the exact one on the side, in case this is the smallest value. But it's unlikely to be, because this will just be 7.7. Well, actually, that's very clear. It actually is the smallest one in this case. So 7.69 over 1. So divide this by itself, which is over that. But I just write 7.691. This over 7.691. These should be very close to 1. So the empirical formula should be pretty much 1-to-1 in this case. So this would be 1, calculate the empirical formula. So 1, so I need to use 7.7 over this. 7.7 over answer 1.01. I'm taking a bit long to answer these, but I'm just doing it because of like the video. So I guess you should be much quicker than this. But yeah, so C, H should be that. Double check that. Yeah, just went to go double check the mark scheme, and it's just pretty much the same thing. So it should be fine. Calculate the molecular formula of W. You know that the molecular formula of this is 78.8, and this is 12 and 1, so that's 13. So what you could do is just do this 78 over 13 actually. 78 divided by 13. And that gets you 6. So you know each one is just give 6 each. So if you do, or just 6 of this, so C6H6, that's 12 times by 6 plus 6, and that should give you 78. And yeah, that should be it. Maybe I should just write this here, because you want it to have it on the line, equals 6. So just do 6 of C6, H6. But that is your answer. So yeah. One isotope of sodium has a relative mass of 23. Calculate the mass in grams of a single atom of this isotope of sodium. So one isotope of this has a relative mass of 23. Calculate the mass calculate the mass in grams of a single atom of it. So you should just divide it, I'm pretty certain. If the whole thing of the relative mass of this is 23, because usually you do 6.0 something, 6.022 times 10 to the power of 23 times by, we'll just say x, for example, that would give you this, I'm pretty 23. So if I just want to get what x is, and by that I mean the mass in grams, 23 over 6.022, or they actually given it as 6.023. I don't know why it's done it. It's probably this is meant to be to the power of 23, not 1023. So 6.023, let's change that here, times 10 to the power of 23. You should do it as mR over L. Gets you the mass. And that equals 23 over 6.023 times 10 to the power of 23. And that will give you 3 point, calculate the mass in thing. Hold on. This looks really, the mass in grams of a single, of a single atom. Yeah, that's okay. That's definitely, this is definitely right then, yeah. Single atom, I was about to say, to the power of minus 23 is quite small, but 3 point, the lowest amount of 1, 2, 3, 4, 23, 2 significant figures there, so you can just write 3.8 times 10 to the power of minus 23 is equal to the mass of one atom of the isotope of sodium. Say what is meant by empirical formula. It's the simplest ratio of atoms of simplest ratio of elements of elements. What's thinking about atoms? Simplest ratio of elements in compound. If I check, should be right. No, this is wrong. The simplest ratio of atoms of each element in a compound. So simplest ratio of atoms of each element in a compound. A chromium compound contains 28.4% of sodium and 32.1% of chromium by mass. The remainder by being oxygen. Calculate the empirical formula of this compound. So, chromium compound contains 28.4% of sodium and 32.1% of mass. The remainder being oxygen. Okay, cool. So you have Na. I don't know the symbol for chromium. Pretty sure it's just Cr, I think. I think it's Cr. Let me just double check the periodic table. The period. Yeah, it's just Cr. Alright, it's fine. Yeah, so you have chromium here, and the last of it was oxygen. Yeah, so make sure to write it as a standard element, not O2, just O, because you're getting the empirical formula here. So you're just gonna get the standard, or it's just on its own, just the element by itself. Because remember, it's the ratio of atoms of each element, so not the diatomic state of it. So Na, we have it here as 28.4. Chromium is 32.1. And then oxygen is said the remainder being oxygen, so you can just do 100 minus 28.4 minus 32.1. And that should give you, well, that gives you 39.5. So you can get out here 39.5. Yep. So divide by 14. Divide that by whatever the atomic mass of chromium is. Divide this by 16. I know, so 28 point. Let's do this because I know that Na is always 14. No, it's not. I was thinking about nitrogen. Nitrogen is 14. Sodium should be 23. I made that mistake for other questions. I'll come back and do that later anyway. Over 16. I know this is definitely 16. It's about 28.4 over 23. That gives you 1.23. So on. Write, if you want to write that, the exact value, 132 over 115, in case this is the smallest value, which could be, unless this is a really big number, but I think it's in the transition metals, the third period, so I don't think it's that big, but we'll see. 39.5 over 16, or over 16. 79 over 32, let's write that over here. 2.46875. That's not really a long number anyway, so you can write that if that was the smallest number, but it's not. So far, sodium is. Chromium, I don't know it off by heart. They usually give you a periodic table in the exam. So chromium would be 52. So this is over 52. So we'll see. This will be the smallest one. The numerator is smaller than the denominator, so this one will definitely be the smallest one. So 32.1 over 52, and that equals, so just 321 over 520, 0.617, so on. Divided by the smallest one, which is 0.617, I'll get you 1 here, 0.617, 0.617 So I want to get the exact value because I'm not rounding them yet. So I can just use this here. 142 over 115 equals, that's your answer. Answer over 0.617, 0.617. That equals that. So that's a 2 value. So just, you can really round that one to 2. 3.001, but that'll just be 2 realistically. 2 point, this isn't a really large number, so you can just 2.4 6875 over 0.617. That gets you 4. So yes, Na2 4. And that's it.